please.
Hi, everybody. You can hear me, I presume? Okay. So yeah, I'm gonna try to answer this question. Usually when you have a title with a question, there's a lore that the answer to the question is no. But today you'll see that the answer to the question is yes. And this is based off mainly work in progress, should appear as soon as I get my act together. And this is work with Jeremias Aguilera Damia, Dion Aninos, Alan Rios Fukelman, and my student Johnny Gleason. So I just want to set the stage. So this talk is going to be about QFT and de Sitter. There's not going to be any quantum gravity turned on. And I think that it's important to make that clear, in particular because we're very confused by just regular QFT notions in de Sitter. I'm going to talk about some of the issues later in the talk. But just know that many of the things that we take for granted with respect to QFT doesn't apply immediately when we port flat space QFT onto the de Sitter manifold. Okay, so just want to remind you that global de Sitter space is a very special spacetime. It's very symmetric. You can write it down as the solution to some embedding formula. Notice this minus. So if this were a plus, then you would have the equation for a sphere. But because of the minus, we sometimes call this the pseudosphere. But this is a very symmetric spacetime. It has the exact same number of symmetries as a sphere. And we like spheres because they're very symmetric. But because of this minus, then the global slices of the spacetime are spheres, and they grow in time. So this is the simplest example of an accelerating cosmology. And it's relevant for the early universe and the future of our universe as well. And many settings of QFT on this manifold are used to study just basic ideas, for example, in inflation, early cosmology. So this is why this setting is very important. So we have a time-dependent and yet still very symmetric space-time that represents a cosmology. And that's what we're going to put our QFT on. Now, the lore that we're going to try to address today is that if you take a QFT and you make that QFT have a global symmetry, then the lore is that that global symmetry will never be spontaneously broken on de Sitter space. It's just a piece of lore that every example that we know of seems to hold true. And the reason that people make this claim is that, well, you may have heard this, but de Sitter space has a temperature. So physics locally looks thermal. And whenever you have a thermal state and a global symmetry, well, thermal fluctuations restore that symmetry. So you might imagine that you break the symmetry, but then if you allow the thermal fluctuations to happen, states get populated, not necessarily at the same energy, and all of a sudden, a symmetry that was initially spontaneously broken gets restored. So the idea is that it's very difficult to break a global symmetry just because of this fact that you will have thermal fluctuations in de Sitter, and that symmetry will be restored. Is that clear? So I'm now going to present you with two examples where this reasoning fails. And the first is going to be trivial, and some of you will complain, which is why I have the second example. Okay? So, and before I go on, I just want to leverage this fact that de Sitter is very close to a sphere. So just by analytically continuing this first guy, we get exactly the equation for a sphere, and you get a very different picture. So this is the Lorentzian picture. You have an accelerating cosmology, spatial volumes grow in time. In the Euclidean picture, everything is compact, and there's no it's not easy to relate these two pictures. So they're very different. But nevertheless, we often leverage this fact that de Sitter space can be connected to the sphere via Euclidean, because we like to build de Sitter invariant states using the Euclidean path integral. This is this Hartle-Hawking construction. So the basic idea is that you put your QFT in Euclidean, you do some amount of Euclidean evolution to prepare the state, say on this slice, and then this is some symmetric slice, which you then attach to Lorentzian de Sitter, and you time evolve that state. And then anything that you can conclude about physics in this state should be de Sitter invariant. This is a way to construct a de Sitter invariant state, and then compute correlation functions in that state as a function of time. Okay? So it's very important for us to be able to solve models on the sphere, because if we can do that, then we can use this Hartle-Hawking construction and compute things in this state built out of the Euclidean path integral using this picture. Okay? Okay, so now let's move on. Let's get to the first example. So I'm going to work in two space-time dimensions. I'm going to consider a QFT with the following Euclidean action. Okay? It's very simple. There are just two fields. There's a field B, which is a scalar, and it's coupled to F mu nu. F mu nu is built out of a U1 gauge field the normal way. And this scalar field, I'm also going to take it to be compact. So if I have B, it's identified. There's an equivalence class of B with B plus 2 pi. So B is a field whose zero mode is compact. The theory also has a coupling constant, and this coupling constant I'm going to call P, and P has to be an integer, as we'll soon see. Okay? So this is the action, this is Euclidean action. I exponentiate the Euclidean action to get the path integral. This theory, because it has a field B and F, it's just called BF theory. It's not a very creative title, but that's what it's called. And it's a well-known topological quantum field theory. The field B, the scalar, and the gauge field A are roughly canonical conjugates to each other. You can see that here because B and A dot, so they're canonical conjugates. And the theory is basically free in that language. So it's very easy to do canonical quantization. The whole Hilbert space of this theory is very easy to write down. Okay, now let me tell you a couple of other things that are important. First of all, because we're going to work in Euclidean, and the Euclidean theory is a two-sphere, we have to deal with flux quantization. So the gauge field has to satisfy this fact over here. So there's this number k, often called the Chern number, calculates something topological about the field configurations on the manifold. And that topological number has to be an integer. Okay, so this combination has to be an integer. And hence we immediately see that if I shift B by an integer times 2 pi divided by P, then this action shifts by the following number, 2 pi I n k. So 2 pi I times an integer. So the action is not invariant under such a shift, but because we exponentiate the Euclidean action, the whole theory is invariant, right? The path integral is invariant under such a shift. So this shift by 2 pi I times an integer, while not a symmetry of the action, is a symmetry of the theory. And since it's a symmetry of the theory, we have uncovered a global symmetry. Okay, so and I want to specify that this global symmetry is only a global symmetry for n from 0 to p minus 1. Why is it only a global symmetry for n from 0 to p minus 1? Well, if n is p, then I get a shift of b by 2 pi. And we said that that was a redundancy. Shift of b by 2 pi is not really a shift. There's an equivalence between b and b plus 2 pi. So a shift of n by p, a shift of n equals to p is a redundancy. And hence, if n is p plus 1, I can relate it to n equals 1 by a shift by 2 pi. So only these n are actual symmetries of the theory. So what that means is that my symmetry, the global symmetry of this theory, is also known as ZP. It's a discrete global symmetry of this topological theory. Okay? Clear so far? Very good. Okay. So now let me tell you what the well-defined operators of the theory are. The well-defined operators of the theory, because b is only identified modulo 2 pi, the well-defined operator of the theory is an exponential of b. And I'm allowed any integer here, m. So m is an integer. And I also have the Wilson lines. So the Wilson lines are integrals of the gauge field A along some curve. And I also, by flux quantization, need this n to be an integer. Okay, so I have operators which are labeled by two integers, um and wn, I've called. And I've included the position of this operator b here, as well as this curve, the curve dependence of this Wilson line here. But because this is a topological theory, there is no dependence either on x or on c for the correlation functions of this theory. Okay. So what might look like a local operator or an extended operator really doesn't have any dependence on either the position of the insertion or the curve of the Wilson line. Now, one more thing that I want to mention is that this operator um is a charged operator under the ZP symmetry that I mentioned before. So how do we see that? Well, very simple. Let me just do a shift of the symmetry by 2 pi over p. That's n equals to 1. If I do a shift by 2 pi over p, then my operator shifts by this phase. And so I see this is the way that you measure the charge of the operator. So these are fractionally charged objects. Now, it's also pretty straightforward to show using the path integral that the lines, the Wilson lines, measure this charge. So if I insert one of these UMs and I try to place W and W dagger above and below, then you can see that this is like wrapping the charge. And wrapping the charge is what we do whenever we want to measure the charge. So again, these W's are the topological operator that measure the charge of UM. You can flip this equation around, actually, and see that UM is a topological operator that measures the charge of the W operator. So the W is charged under a higher form symmetry, and its topological operator that measures the W operator's charge is U. So there are two symmetries, one zero form and one form symmetry. And these two operators are the charge operator of the other. Okay. So one last thing that I want to say about this theory is that these UMs are not all independent. In fact, if I shift m by p, then you can clearly see.
The one-point symmetry are just flat shifts of A. And those, in fact, you're making a constraint there on the topology of a certain sum that you're studying.
Yeah.
Non-trivial.
Yes. I'm doing this everything on the S2. There are no non-trivial cycles. And no. You simply need this charge algebra. And this charge algebra is there even if there's no non-trivial cycle. Okay. Any other questions?
These operators U and W.
Sorry.
Is this like the Hooft loop and the Wilson loop in 2 dimensions? No, maybe not. It's 2 dimensions, so you can't have 2 loops, right? Okay. Yeah. Take it back.
But yeah, so but all it is that there are 2 discrete symmetries in the theory, and they're related to each other. The 2 charge operators measure each other. Okay. Yeah. So now I was getting to the fact that not all of these U's and W's are independent. In fact, if I shift this m by p, the coupling constant, which is an integer, then notice that this phase shifts by 2 pi I n. N has to be an integer. So the phase shifts by 1. So um plus p and um are actually identified. So in fact, what this tells me is that I don't have an operator, an independent operator um for all m in Z. I only have independent operators um for m from 0 to p minus 1. They're p local operators, this theory. And by the same argument, there are only p extended operators. So for n from 0 to p minus 1, and m from 0 to p minus 1. So the operator algebra of this theory is finite. There are only a finite number of operators that I can write down. There are p local operators and p extended operators. Okay. So what is the implication of this fact? The implication is that there are p orthogonal Hartle-Hawking states for this BF theory on de Sitter. So remember, I started this talk by telling you that what we often do is we start in the Euclidean picture, prepare a state by Euclidean evolution, and then attach that to the Lorentzian evolution of the theory. Okay? So this is the standard picture. No insertion in the Euclidean hemisphere. Do a Euclidean evolution, and then attach this to Lorentzian evolution. And that builds something called the Hartle-Hawking state, HH, or the ground state. Now, what we're showing, this is kind of a trivial fact. Many people knew this. I think the interpretation for de Sitter is kind of obvious. And I don't know if it appeared somewhere before, but this is just a conclusion of putting this theory on the sphere. Okay, you can make p of these states. So 0 is just but one of many of these Hartle-Hawking states. But I can insert U1 here. It's a state with ZP charge 1. This is a state with ZP charge 0. This is, and then I can insert up to UP minus 1. And these are p independent Hartle-Hawking states. They're distinguished by their ZP charge, and they're orthogonal. It's very easy to show that they're orthogonal. So what does this mean? This implies that, so this theory has a ZP symmetry. I put it on de Sitter. There are p states. And I want to mention one more thing. Sorry, just in order to make it absolutely clear. So the theory that I'm studying, or that I'm explaining to you here, is a topological theory. Because it's a topological theory, that means that the Hamiltonian is 0. There's no, the theory is a theory of ground states. So all of these states have the same energy. Okay? If they have the same energy, then these are degenerate states, by however we like to describe degenerate. They're in some symmetry algebra. And what this suggests is that I have a theory. It has this ZP global symmetry. And this ZP global symmetry is spontaneously broken on decision. Because the Hartle-Hawking construction, the normal one where I just insert the identity in the Euclidean section, prepares the charge 0 state of this ZP symmetry. However, I could insert any number of these and have a different ZP charge. And that ZP symmetry would then continue under normal time evolution, and there would be no mixing between the states. So often these states, these p-independent orthogonal states, they're sometimes called universes instead of states. But the language of symmetry breaking is absolutely the same, and I think there's no difference. So what this means is if we start with the Hartle-Hawking state, we'll always remain in the Hartle-Hawking state, and the ZP symmetry will never be restored. You'll never populate the other ones because the Hamiltonian doesn't mix between these states. The Hamiltonian is 0. The Hamiltonian never mixes between these states, and the symmetry is spontaneously broken.
Precisely is the definition of spontaneous symmetry. So you might all, like there are local operators that are charged. You could insert some of the views, and now you're mediating position for the Hamiltonian to do that. So if the usual thing people think of is spontaneous symmetry, you can't go from one point on the vacuum manifold to another with the local operator. That's fine. Here are your definitions that you have these sectors and you don't evolve from one sector to the next.
Yeah. So I guess my definition is that my definition is that you can prepare one of these states, and then you won't evolve into another one unless you do some external operation.
So in this topological theory, what's the signature of the fact that de Sitter has a finite temperature?
So this is why I said that this is trivial and that you should complain. This is a topological theory, and it does not feel at all that it's on de Sitter. I could have made this argument on any background, and it would be the same. So you should rightfully complain that I haven't shown very much because the theory is topological, and it doesn't feel that it actually lives on de Sitter, and it doesn't feel the temperature. So you won't get this restoration mechanism, which is why I included the second example. Okay. So very good. I even prepared a slide about this. You should complain about me deriving any lessons about de Sitter by studying this topological quantum field theory. The physics is independent of the metric, so this theory doesn't care that it lives on de Sitter. And the conclusion that I draw is independent of the background. So the fact that I have spontaneously broken the symmetry doesn't tell you very much. One interesting thing, though, is that this is a two-dimensional theory. And there's also a law that you can't spontaneously break symmetries in 2 dimensions due to Coleman. But this example evades that because this is a because this is a discrete symmetry. Okay. Any questions before I move on? So that's
just a statement about Hilbert space on the circle.
yes.
You can't really restore anything, so you can't break anything.
Yeah. But this is going to set the stage for the next example. So we're going to do a less trivial example, and then hopefully we'll conclude that you can still do this in a non-trivial. Any other questions? Okay. So how do we proceed? Okay. Well, if we can somehow identify a QFT whose infrared is governed by BF theory, then maybe we can simply port the results from the previous section to de Sitter. That's one idea. But I want to mention that this is very subtle, and we have to proceed with caution whenever we're dealing with de Sitter. And that's because basic notions that we take for granted, quantum field theory in flat space, doesn't port to de Sitter. Okay, I'm gonna review that now before we go on to the next example. Why is this subtle? Why can't we just take some theory whose IR is governed by BF theory and then simply port the previous results? Well, the main reason, and yeah, the key difference is that de Sitter and Minkowski space, the basic notions are very different. And the main thing that I want you to remember, or maybe appreciate if you have never thought about how QFT works on de Sitter, is that the Wilsonian paradigm on de Sitter does not really work. Okay? So let me tell you why. So in flat space, let me show you a process that that you can imagine cooking up in flat space. So you take some particle of mass m0 and imagine that it decays to two particles of mass m1 and m2. Okay? Now, this process is forbidden in flat space if m0 is less than the sum of the rest masses m1 and m2. And that's a very simple consequence of energy conservation. There's a momentum preserving delta function. Momentum preserving delta function means that if m0 is less than m1 and m2, you will never have the kinematics to form such a diagram in flat space. Okay? However, in de Sitter, the amplitude of such a thing happening is not zero. It's not zero even if m0 is less than m1 plus m2. These rest masses, the sum of the rest masses can be greater than m0 because remember, de Sitter is a time-dependent background and there's no energy conservation on a time-dependent background. I'm allowed to violate energy conservation because there is no energy conservation. So the consequence of this is it's never possible to fully integrate out heavy states in a QFT because the UV never fully decouples from the I. If I start with some low energy state, I can always populate higher energy stuff in de Sitter as I time evolve because Hamiltonian is time dependent. It's the same understanding that we have when we think about thermal field theory. Thermal field theory, energy is not conserved. I'm allowed to have thermal fluctuations that populate higher energy states, which is why you imagine that if you have symmetry breaking, you might be able to restore it using thermal effects. Same idea. I'm going to make a more precise version of the argument because, of course, I talked about amplitudes. In de Sitter, we don't think about scattering amplitudes, but there's a analogous way to think about the non-existence of such a diagram in de Sitter from the perspective of a correlation function. So in an interacting theory, I can always write my correlation function as a density integrated over a free correlation function where I integrate over the mass. And unitarity forces this density to be greater than zero. This is known as the Shalane-Lehman representation in QFT. And a generic QFT, this density looks like this. There are some mass poles, and then there's a cut at 2m squared, where m is the mass pole, and the density is positive there. And the fact that you have this separation between the poles and the cut is what makes this kind of amplitude not possible for these kinematics in flat space. Okay? However, in de Sitter, we don't really care about rho of m squared. Instead, we care about working with the invariant notion of the de Sitter symmetry group, which is SO1 d minus 1. And there you have the Casimir. It's much like in ADS. Casimir and the mass are related in the following way. And you can see if m is pretty big, then del squared is minus m squared, so delta can be imaginary. And this nu is the quantity that goes in the density. And this rho of nu for a generic field theory is very different from the diagram I showed you in flat space. In flat space, you have this cut that separates from the mass poles. But for a generic interacting QFT, this rho of nu has support on the entire real line, which implies that this amplitude is not zero. Okay. So that's the argument. So the upshot is that we can't really trust that IR physics decouples. So if we're going to show that spontaneous symmetry breaking happens in de Sitter, we have to do it from the full UV theory without making any simplifying assumptions that we can integrate out states and work in the IR phase of the theory. Okay? We have to work in a full UV theory and come to the same conclusion. Okay? Is everybody in agreement? Yeah, I'm saying that.
But I mean, this thing works not because we really decouples, but rather we can classify things that are important and that are not important, relevant, irrelevant. You are saying relevant, irrelevant classification doesn't exist, is it not?
I would say, I'm not going to be so strong. I'm going to say that we don't know what we're doing. Just taking this picture from flat space, relevant and irrelevant, integrating out, thinking about what is important at large distances, all of that stuff hasn't been shown in de Sitter. There's very little work that really fundamentally shows how you would, what the long distance physics should be. De Sitter is a theory with a scale. So really, it's different. It's
similar to a time-dependent Hamiltonian. We have a time-dependent Hamiltonian. This will here topic with the energy. That's some of it. Yeah, I do see that.
Yeah. So what I will say, I don't want to make any strong statements. I'm not going to say that like it's wrong. I just want to say that okay. The field of quantum field theory on de Sitter has a lot of people fighting about very many different things. And I think part of the reason why they're fighting is that some people take one thing as the truth and other people take something else as the truth. And they don't agree on those two different aspects. So I just want to proceed without making any assumptions so that nobody can get mad at me. Is that okay? Yeah, it's very subtle. I think that this kind of classification, what is the notion of relevant, what is the notion of irrelevant, needs to happen, but I don't think there's a satisfactory picture yet. Doesn't mean that it can't be done. It just needs to happen. And this is just QFT on a fixed de Sitter background. This is not even, we're not even talking about what happens when you couple gravity. Okay, so next I'm going to explain to you that, so we need to be very careful. I'm going to give you an example that very closely mimics the topological example from before, but in the next case we're going to work to show that spontaneous symmetry breaking can be demonstrated in a full UV theory where we have full control. We're not going to make any approximations. We're not going to integrate anything out. We're going to work with a dynamical field theory. The Hamiltonian is not zero. It's not a topological QFT. And we're going to come to the exact same conclusions as before. Okay, that's the promise of this talk. Okay, so what is the second example? The second example is known as the Schwinger model. Schwinger wrote this down. It's a slight variation of the Schwinger model. So the Schwinger model is the theory of a Dirac fermion in 1+1 dimensions, coupled to a gauge field. And the gauge field is F mu nu as before. I have A mu and I have this Dirac fermion. And this is a slight variation of the Schwinger model that was studied in 1962. I'm now allowing the gauge field coupling to be so this number P in front of A is the charge of the fermion in fundamental units. And P has to be an integer because I'm taking the manifold, the U1 of the gauge group to have volume 2 pi. P measures the charge of the fermion on that manifold, so P has to be an integer. And Schwinger in 1962 studied this model with P equals to 1. Okay? But that doesn't stop us from having a fermion of charge 2 or 3 or 4. We're allowed to do that. And this number Q here is the gauge coupling. And the gauge coupling has dimensions of 1 over length. So this theory in the IR is strongly coupled. But we'll get to it. Okay, so this theory has gauge invariance. So if I rotate my Dirac fermion by a local gauge rotation e to the IP alpha psi, I can undo that by a gauge rotation of A. And there's also a chiral symmetry of the action, which is anomalous. It's a famous chiral anomaly. So if I rotate psi by, if I rotate the top and bottom components of the fermion separately, I have also a conservation law, classical theory. So this gamma star is what is sometimes called gamma 5 in 4 dimensions. It's 1 and minus 1. Okay, so let me just tell you what happens under a local chiral rotation. So if I now let this beta not be just a pure number, but if I let it to depend on space, then my action shifts like this. So there's a piece over here. And then I get beta del squared beta. And then this, what looks like this BF term from before. Okay? Now, of course, if beta is sorry, two things. This piece comes from the classical rotation, and these two pieces come from the anomaly. So this comes from varying the classical action, and these two pieces come from measuring, rotating the determinant, the measure of the path integral action, d psi bar d psi. So the anomaly picks up this coupling to F, and there's also a second derivative term here for beta. So this is what's responsible for the chiral anomaly, this kind of rotation of the fermion measure. Now, if you see, so now beta, if we take it to be an integer, or if we take it to be a pure number, this term goes away, this term goes away, and we're left with this background coupling to epsilon mu nu. And now remember that the thing that multiplies beta is an integer by flux quantization. So if I take beta to be 2 pi n over 2p, for n from 0 to 2p minus 1, this is, again, a symmetry of the theory. So I have a discrete chiral shift of beta in the theory where p is not equal to 1, which looks like I have identified a Z2P symmetry of this theory. It's not quite Z2P because remember, if n is p, then I have e to the I pi gamma star, which is just equal to minus 1, which is the same as e to the I pi. So that's just a gauge rotation. So the second half of those rotations are related to the first half by a gauge rotation. So actually, I only have ZP. This theory has a ZP global symmetry, just like before. So beta for shifts, chiral shifts beta by pi n over p, for n from 0 to p minus 1, are actual symmetries of the theory, symmetries of the path, not anomalous chiral rotations. Okay, the theory has a Dirac fermion, and the chiral rotation is anomalous. However, for these discrete chiral rotations, the symmetry is non-anomalous. So this theory has a ZP. This theory has a ZP global symmetry. And if P is 1, which is the model that Schwinger studied, there's no global symmetry. Just the chiral symmetry, which is fully broken by the anomaly. Okay? So we're going to study this model. We're going to solve it via Bosonization. So the typical Bosonization map is to take the current for the U1 global symmetry and bosonize it to epsilon mu nu d nu times some boson. And the chiral current will be the derivative of the boson with some i's. This is the typical bosonization map. And this B is a compact scalar. B is identified with B plus 2 pi. You can see that because these currents only depend on derivatives of B. The zero mode of B doesn't ever appear in the bosonization map. And for this map to work, in fact, you actually need B to be compact. And the size of the scalar zero mode is 2 pi. Okay, so now let me write down the bosonized action. The bosonized action is a standard kinetic term with 1 over 8 pi. So it's not canonically quantized. There's again the f mu nu squared term. And then all of a sudden, there's the BF term that appears, exactly as before. And the argument that people make in flat space is that, okay, now that I study this, at low energies, these derivative terms are irrelevant. And at low energies, this theory is governed by the topological quantum field theory that I described in the first part of the talk. So therefore, this theory at low energies will have p states. And those p states are distinguished by their topological charge, their ZP charge, exactly as I described before. But as I mentioned, in de Sitter, we have to be very careful. We can't just take the IR physics for granted. So what we're going to show is that this full theory has the same structure. Okay? So just to recap, this B is quantized, B plus 2 pi, and the ZP chiral symmetry of the fermion appears as this 2 pi n over p shift of B. So the 2 pi n over p shift of B is the avatar of the preserved chiral symmetry of the theory. If P were 1, there would be no global symmetry in the theory. Okay? Is that clear? Okay. So this is just what I mentioned before. In flat space, we would argue that the BF theory is the IR important physics. But here we're in de Sitter, and we're not going to just take that for granted. Okay, so to proceed, I have to convince you that this full Schwinger model, or at least this bosonized Schwinger model, has the analog of this operator UM and WN that I described before in the topological QFT. Okay, and they have to behave exactly as in the BF theory for my conclusions to work. Okay, so it's possible to do that, and all we have to do is consider the 1 and 2 form conserved currents associated with the ZP symmetry. And I can write those down exactly for this model. It's very simple. I just have to construct these two objects. So this is the 1 form current. So I'm using the star language. I hope that's okay, the Hodge star. But so this is a 1 form. You can see that it has 1 index conserved current built out of A mu. This object is not gauge invariant because it just has an A. So I'm never going to write just star J1 anywhere. I'm going to have to integrate it along the line. And I have a 2 form conserved current whose star is a 0 form, which is P over 2 pi B plus this combination with the gauge field. And the conservation of these two currents, are just the equations of motion of the classical Lagrangian I wrote before. So here's the classical Lagrangian again. And I leave it as an exercise to all of you to just show that the conservation of these two currents are just the equations of motion that I would derive by varying with respect to B and A mu. Okay? Now,
This last bit about current conservation, very specific. So discrete symmetry. So I guess this was really that you can build topological operators out of these.
Yes,
things,
yes.
And then you, at intermediate steps, to demonstrate that those things are topological, would use this.
Correct.
For instance, the second thing, the conservation of that there is no, that really is reflecting the existence of a shift symmetry of the first line, including the non-VF term interaction, which would be broken by instant topics.
Correct.
Okay.
Correct. All of that is correct.
So somehow, even though you have the kinetic terms for beta and F, you really do have the one-point symmetry. Okay.
Yeah, that's the nice thing, that this that you can just show that you can build the topological operators for this theory, even though you have the kinetic terms. There is a subtlety, which I'm going to get to, and I'm really glad that Shota brought that up in his talk, which we'll get to. Okay, so the claim is that I can build topological operators by exponentiating these currents. So just like before, I have star J2. I have to multiply by 2 pi I m over p, and this is how I build this operator un. And with the one form, I integrate it over a current, over a curve, and I need to multiply by 2 pi I n over p. And these are well-defined topological operators. And they have the same algebra as the algebra I showed you for the BF theory. Okay, but so the conclusion would be that now I can just run the game again. In this theory, which is non-topological, I have p orthogonal Hartle-Hawking states using the ZP symmetry, and this is evidence that the ZP symmetry is spontaneously broken. So 0 would be inserting the identity in the Euclidean path integral. 1 would be inserting U1, and p minus 1 would be inserting UP minus 1. And these states are orthogonal. This is the way that we conclude that this theory has a spontaneous symmetry breaking of the ZP symmetry, ZP global symmetry. But of course, I skipped the details of this. But as Shota mentioned in his talk, I can't just exponentiate these operators and expect in a QFT to just say that these operators are well-defined. These operators are extremely ill-defined because I haven't told you how to regulate it. The only way that I can really conclude that this works is that I have to give you a way to regulate these operators, and doing that is extremely subtle. So of course, this operator, this star J2, is a local operator, and I told you that if it's a topological operator, it doesn't really depend on the place where I've inserted it. And same with this curve. Well, I've skipped the details in what I've told you, but really, in order for me to define these operators, for example, for the local operator, I can't just insert the local operator locally inside the exponential. I have to cut out a disk. Cutting out a disk introduces some metric dependence around the disk, and of course I have to define a wave function normalization for this exponentiated operator, and all of those things one has to check whether or not they go through, and you have to trust me now. I'm not going to show you. I don't have time to show you in this talk. You have to trust me that, in fact, this works. And similarly with the extended operators, that we can define regulated extended operators, and the algebra, which is that these operators are orthogonal, actually works out. And an important fact is that for this to work out, so for example, to show that these two states are orthogonal, so instead of having an operator inserted at a point, I have to insert it, smear it over some disk. And so that's the bra and the ket. Well, I guess this is the bra and this is the ket. So for both of them, I have to smear over a disk. And to show that these are orthogonal, we require that the disks are not overlapping. In BF theory, we never had to do this. It's really important that we ensure that the disks aren't overlapping when we compute these norms. So really, there is some creeping UV physics that you would see if, for example, these operators got too close together. So, but if you take all of that as a given, then indeed you get this kind of algebra, and the states are orthogonal, so long as this ensure this fact.
Well, so far, again, all the formulas you written were in plastic.
No.
But
Take this to be the sphere.
what about the reduced that to bring them on over?
Also take it to be the sphere. It works. There's a great paper by, that we discovered from 1988 by a person with only one paper. His name is Kamilas Jayawardana, who solves the Schwinger model on the S2. And when we discovered this paper, we were very excited because we understood that we could use this to understand what happens with the Schwinger model on de Sitter. Just making the charge not equal to 1 is one additional thing that we can do. But you can put this model you can put the Schwinger model on the sphere or de Sitter and solve it, just like Jayawardana. And just like Schwinger did in flat space. You can solve this on the sphere. That's very important. You can solve it fully non-perturbatively. This is the only reason why we trust these results. If we weren't able to fully non-perturbatively solve this model, we wouldn't trust anything they were saying. Even these topological operators, there's metric dependence in them.
So for the Euclidean hemisphere, you can smoothly groove that with de Sitter, but you can also smoothly groove that with a flat cylinder. So does your computation distinguish these two cases?
It won't distinguish for these topological operators, but it will distinguish if you insert other local operators and measure correlation functions. So we can do that. So what's interesting about this theory is that I also didn't say this. So these are states. So first of all, these are orthogonal, but then you might ask, okay, if I compute correlation functions in these states, are they de Sitter invariant? And the answer is yes. And those local operators would distinguish between whether or not you put the cylinder in between or not. So yeah, but we can compute local operators in these states, local operator expectation values, also to any order and fully non-perturbative. Okay, so what I want to say is, so basically what we've shown is that in this model, which has a ZP global symmetry, the ZP global symmetry is spontaneously broken. There are P inequivalent, de Sitter invariant, Hadamard, Hartle-Hawking states, and it's a robust fact about this theory. So and this goes back to the question Qiming just asked me. Correlation functions in these states, we can compute them. They're de Sitter invariant, and there's no funny business. They have the standard singularities. These are not alpha states. That's why I said Hadamard. They're just good, honest to goodness QFT states for a de Sitter QFT. Okay, now another interesting thing is that the mechanism that we use to derive that this theory has a spontaneously broken global symmetry. So I didn't use these words because I find it a little bit abstract and maybe not so illuminating, but the words that you can use is that this theory has two symmetries, right? So a zero form symmetry and a one form symmetry. And and all you need in order to ensure such a breaking, this universe structure of the set of ground states, is that you have a zero form symmetry and a higher form symmetry which share a mixed anomaly. And if you can find a theory that has that, then what we would say is probably with high likelihood that you have spontaneous symmetry breaking for this theory. On any such a theory would exhibit spontaneous symmetry. And in fact, we're now trying to repeat this for 4-dimensional QFT on de Sitter, which would exhibit the same type of phenomenon. And also going back to what Shota was mentioning, we're also interested in trying to understand what happens if we couple this theory to gravity. So the argument that Shota made for these topological operators not existing because the curvatures become strong doesn't really, it's not really a problem in 2 dimensions, because in 2 dimensions, the Einstein term is topological. So it doesn't tell you that, so really the only thing that you have to confront for this, to see this symmetry being restored by quantum gravity effects is to understand the topology changing operations. We're trying to see if we can understand that a little bit better. So we'll report on that soon. That's what I have to say.
Please ask questions.
Very naive. So at every time slice, a de Sitter looks like a sphere. Now, I mean, spatial is sphere. And typically, we believe that there is no spontaneous symmetry breaking in a finite volume, right? Does that play any role here? I mean, the fact that, no.
So yeah, this universes thing is very robust. So you can do it at finite volume. So some people don't like to call this spontaneous symmetry breaking. That's why they call this the universes mechanism. It's really robust. It happens at finite volume, finite temperature, happens in de Sitter. So some people would argue that you should think about this as separate to the usual spontaneous symmetry breaking. You know, be a little bit provocative.
There's no possibility of a tunneling. Typically in a finite volume, tunneling.
Yeah. Just in the QFT language, it's
potentials are not like that.
No. It really has to do with the fact that you have a discrete symmetry. There's a discrete higher form symmetry. They share a mixed anomaly, and when you have that, it's very robust, even a finite volume.
Just a comment. I mean, I think even the words that you say there, this is exactly the phenomenon that protects the ground state degeneracy of fractional Hall states.
Yeah.
Where the relevant symmetry is magnetic translations, and yeah, there's a one form symmetry and there's an anomaly, and yeah.
Any other question or comments?
So just to double check, so in this case, you still don't have the symmetry restoring regime. Okay, so, okay.
Yeah, this is a spontaneous. This symmetry is spontaneously broken on de Sitter. So no thermal fluctuations, no fluctuations whatsoever restore the symmetry. But what's nice is that we showed that even there's no funny business. Even in the full UV theory, this happens. We didn't have to just say, okay, flow, then the relevant physics is the IR phase of the theory, because you could get around that argument by saying, well, in de Sitter, there's never a full decoupling. That's why we really wanted to solve it in the full theory.
So is there any other question? If not, let's thank speaker again.